Hi everyone, my name is Grace Crocker. Thank you for joining me to talk about a pilot study of an interdisciplinary project for architecture and civil engineering students at Clemson University. I'm a PhD student in civil engineering at Clemson. I worked on this with my advisor, Dr. Brandon Ross. He's a civil engineering faculty at Clemson. Dr. Michael Carlos Barrios Kleiss also helped us with this. He is a associate professor of architecture at Clemson. Also, Dr. Zakumis and Alami Khorsani, helped us kind of conceptualize all of this and plan it all out and implement it. They're both civil engineering faculty at the University at Buffalo who we are working with to do a much larger NSF project that's all about interdisciplinary collaboration between architects and civil engineers, both in education as well as application in tessellated structures, which I'll talk to you a little bit about a little later in this presentation. So the things that we're going to talk about during this presentation are our background for the project. I'll tell you about the project that the students did, who the students were, and what the logistics of carrying this project out were. Then we'll look at some of the student feedback that I got, as well as some challenges we faced while we were trying to implement this project. And then finally, we'll just wrap it up with some conclusions. So first, I just want to talk to you about why we did this project. A big part of why we're investigating collaboration between architects and engineers in the first place is just because of kind of the age-old trope that they don't get along very well. They don't work together very well. There's kind of this perception that architects maybe, I'm sure you're very familiar with this already, I'm just telling you things you already know, that architects, have crazy ideas and then engineers are stubborn about trying to make them work. And so we just thought maybe we could investigate better ways to start this collaboration at the undergraduate level so that students are better prepared to interact as interdisciplinary collaborators and will be ready for it when they enter the workforce. So in order to investigate this relationship, what we really need to do is figure out what makes a great interdisciplinary team member. So the two specific qualities we're going to be looking at are interdisciplinary competence and teamwork effectiveness. So let's define those. Interdisciplinary competence is something that is defined by Latuca et al. They developed a survey in order to measure this interdisciplinary competence, which is something we're going to be using to try to measure this outcome for students. But there are 8 dimensions of this competence, and they're all kind of related to defining disciplinarity and understanding the student's role on the team. So awareness of their own discipline, appreciation of how the disciplines differ, how can they find common ground with the students that they necessarily aren't the same discipline as? Do they understand the other discipline's roles? Can they themselves have the integrative skill to go back and forth and kind of help other disciplinary students? And then teamwork effectiveness is something that is a lot more established already. We're specifically going to be looking at the model set forth by the developers of the CATME, which is a self-evaluation and peer evaluation that's used to evaluate teamwork effectiveness. It was developed by some researchers at Purdue. And basically this has 5 qualities that make a student or an adult an effective team member. And this team member would contribute to the team's work, have relevant knowledge, skills, and abilities, interact with their teammates, keep the team on track, and expect high quality work from the team. So the overall objective for this interdisciplinary project that we wanted to have the students do was to observe how this project between architecture and civil engineering students might impact their teamwork effectiveness and interdisciplinary competence. So I mentioned the CATME and the Interdisciplinary Competence Survey. would be instruments we could use to measure this, and that is what we did in the full-blown experiment that we did. But in order to plan out the interdisciplinary project, we first wanted to do a pilot study. So the results of the experiment are going to be published in a forthcoming journal paper, but for today we're just going to be talking about the pilot study itself and how that went. So first, I just want to talk to you about how we set up the project and who participated in it. So we had 12 total students. 8 of them were from my architecture class, Structures 1, which is kind of an introductory structural, very basic introductory structural analysis class for architecture students. And then 4 of the students came from the structural engineering course, structural analysis. It's more in depth, but these are about as close as you can get to the same class in the architecture and structural engineering disciplines at Clemson University. So we had 12 total students, 4 groups of 3, and the ratio was 2 architects to 1 engineer. And the primary reason for that ratio was just that we were limited in only having 4 total engineers. The way the participants were selected was not quite as rigorous as what we did for the experiment the following semester. Since it was just a pilot study, we used all of the honors students in the structural analysis class that we were using. So they just had this as like a special honors project that they had to complete. And then the students in my structures class got to choose from 3 different project topics because we were limited in the number of engineers that we had. So the 8 students that participated from the architecture department were self-selected essentially. So then we have our project logistics. So this project was conducted a little while ago, fall of 2020, which you may recall was kind of in the height of COVID. So this entire thing was virtual, which presented some challenges, which we'll talk about in a few minutes. The project length was 3 weeks long, and the problem statement for the students was that they had to design a post-tension precast TeSA wall. I'll explain what that means in just a moment. It had to have 2D regular tessellated patterns, and it had to support 75 kips of shear force. And then we also provided them with geometric and material requirements that they were required to use. So, like I said, I would explain what TeSA is. So let's give you a little context. So tessellations, if you're an architect, I'm sure you're already very familiar with this, but just to refresh your memory, tessellations are repeating geometric patterns that have no gaps or overlap if you're using the strict definition. And typically in architecture, they're used as an aesthetic feature. So this would be an example of a geometric tessellation on paper, no gaps, no overlap, the strict definition. But then we have some examples of aesthetic tessellations that have been used in architecture throughout history. Typically they're just used to make the facade of the building more beautiful. But TeSA, which is what we're investigating in this big project that we're working on, it kind of puts a engineering spin on the architectural use of a tessellation. TeSA stands for Tessellated Structural Architectural Systems, and the idea is that we apply these tessellations in load-bearing structural elements. So, for example, we might have these separate, discrete eye-shaped tiles that all interlock. There's no binder or connecting element of any kind other than just the nature of the geometry just holds them in place. So this would be an example of a one-dimensionally interlocking tessellation because this eye-shaped tile is restrained from translation in one dimension. So going back to the students' project, at the very beginning we had an introductory Zoom meeting where the engineering students were able to meet me. I put all of the students in their groups here and I gave them a more in-depth explanation of TeSA than I just gave you so that they would know what their project was all about. About halfway through the 3-week project length, we had some halfway point check-ins via Zoom where the students were able to explain their thought process to me, show me what they were working on, ask me any questions that they had, and I would kind of, stop them if they were going way off track and nudge them in the right direction. And then, of course, they were able to make additional meetings with me if they needed to ask other questions. And at the end of the 3 weeks, they had to submit a 5 to 10 page report on the technical design and their design process. And then they gave us a short Zoom presentation for a small panel. It was myself and 2 structures faculty members. So, the students were able at this time to give us any feedback that they had on the project, and that's what we're going to talk about next. I also gave them an example that they could use kind of to guide their design, because this is something of a, I hate to use the word novel, but it is something of a novel idea in engineering. And of course they didn't already know how to design this because nobody really knows how to design this. So I gave them this really simple example that kind of showed them how to find the critical sections in their design, which just means the section that has the least reinforcement going through the wall. And just to give them an idea of what a tessellation in this application might look like. So I just wanted to show you guys that. And these are the designs that they came up with. Before we get to the feedback that they gave me on the project, I wanted to show you what their products were, basically. So, some of them were kind of simple, kind of similar to the example, like this one that's on the screen now. And then I noticed they kind of got more creative as they went. So, of course, these are pulled from the students' reports, so they all look a little bit different, but we really got some interesting designs, I think. I love the one on the far right. They said it was supposed to look like fish scales. I think they achieved that aesthetic. And it really challenged us as the instructors as well, because we had to come up with a completely different design method for the one on the far right, because the method that we had come up with the critical sections didn't really work for this example. So it was a good challenge for everybody involved, and that includes the instructors. So finally, let's talk about what the students thought about this. So I noticed 2 themes really in most of their responses, and that was the interdisciplinarity of the project and observations about that, and also the observations about the practicality, the more practical application of the things that they've learned so far in their programs. So on the note of interdisciplinarity, we had an architecture student that said it was a good exercise in going back and forth with an engineer, because that's not something they've experienced in their internships so far, but they know further down the line in their career that's something they're going to have to deal with. And then in terms of the interdisciplinarity of the actual content, we had a structural engineering student say that in their classes so far, it's all been idealized monolithic walls and beams and things like that. So this was the first time they've gotten to design something that had that level of architectural complexity. So that was a new experience for them. And then, like I mentioned, they made some comments about how practical the application was, which kind of made me laugh, because this is such a new idea and it probably won't be used practically in industry for a little while. But in terms of the things they've already done, this was a real world topic for them, as this architecture student said. This structural engineering student said they're getting their architecture minor, so they're already interested in the interdisciplinarity. But she said that it was cool to jump into architecture with something that was more practical. And then finally, we had another engineering student that said, even though this wall is idealized to a certain extent, this was the first taste of real design that they got to do. Most of these students were sophomore or junior level students, so they'll be getting into more intense design classes in the next couple of years, but this was kind of the first taste they got of that. So naturally, we encountered some challenges while we were implementing this project. Like I said, it was during kind of the peak of COVID, and we had to conduct the project completely virtually, which meant the students couldn't meet and work together. They were having to send their designs back and forth. We had, all the Wi-Fi problems you could have when we were trying to have our meetings to check in and introduce the project topics, all those good things. And then we also had to organize this project with 2 separate courses in 2 separate departments. So I had to find an instructor who was willing to share students with me, which for me was easy because I kind of knew I had a collaborator before planning it. But in a different situation, you might have to find somebody and get them interested in participating in this. And you also have to organize who's going to do the grading, or are you going to grade separately your own students? So that was something we had to work out. And also just the timing was kind of difficult. We didn't have our courses meeting at the same time, so we had to organize meetings outside of class time. We had to do our final presentations at 7 p.m. the week before Thanksgiving. It was a challenge, but that would definitely be made easier, I think, if in-person meeting was possible. We also had a limited number of participants. As I mentioned, there were only 4 engineering students that were available during the semester for this project, which limited the number of architecture students I could have participating in the project. And there was also limited time. We had to cover other things in our classes. As I'm sure you understand, you've got to get through the required curriculum before you can do some of this other fun stuff. So we only had 3 weeks to do this, and some of the students said, if I just had one more week, they wanted that one more week to iterate their design one more time. So that was the last challenge that we encountered. So I just want to wrap up with some of our conclusions. Despite the challenges I just talked to you about, overall, we considered this project a very good success. The students responded really well. They seemed to enjoy it, and we found their designs very interesting. In the future, if possible, and these are things that I considered while I was doing the experiment the following semester, which you can read about in a forthcoming paper, I would provide them with one more week if they have this level of deliverable. I would give them one more week to work on it. I would also conduct everything in person if possible, particularly just letting the groups work together instead of having to do everything over Zoom and email. I just think it makes them more time efficient if they're able to just sit down together and work. I would also allow all the students to participate. Unfortunately, we were limited for the pilot study, but since they seem to enjoy it and respond well to it, I would definitely want all of the students to get the experience, not just a third of my course. So that's all I have for you. The NSF is funding this whole project that this is just one small part of, that we're working with the University at Buffalo on. And also I want to just thank Dr. Cousins, who is a professor at Clemson. He's the one who let me borrow some of his structural analysis students for this project. So I really appreciate his support. So thank you all for taking the time to listen to this presentation. I hope you enjoyed it. Please contact me if you have any questions or comments about any of this. I'd love to hear from you. Thank you.